All right, so for the first question, I didn't do the ionization of water, so I recalculated that and I got about a 7. And then for the second one, I got a very similar pH, but this much more clearly shows uh, the decrease in pH that happens when you add the acid to the solution. For question 2, I'd make a frame out of the peg. And this would create it's a biomaterial, so it would create a framework, and I would coat it in the fibronectin, and that would direct the fibroblasts to grow here in the shape of the M. Then for this one, I would do induce pluripotent. This is because the embryonic stem cells can form teratomas, which you don't want. And then the iPSCs are pluripotent, which means they can specialize into any kind of cell type. And you can also create these stem cells from the patient's own like skin cells. Like they would have to donate their cells, and you can reform them into stem cells and then respecialize them into anything. So it kind of all around makes induced pluripotent stem cells the better choice. And I had a very similar answer to that. I didn't mention they were pluripotent though, so. Okay, for the next one, I just switched them. Have cysteine going against and glutamate going with the gradient. For fentanyl, this one would be the atom that gets protonated, and at a pH of 7.4, it would still be protonated because it's below the pKa, which means it have a net charge of 1 plus 1. For 6, this is my original answer, but I didn't explain it. But if X has a stronger cohesivity, they will sort of form a colony here, and then Y would form its sort of own colony around it. And this is assuming that XX cohesivity is better than YY, which is greater than XY. This would be the least cohesive, so that doesn't really happen a whole lot here, whereas it happens significantly more here. And this would be an example of where XX and XX and YY are equal, like they're equally cohesive. But in this case, it would be B. So for this one, the longer yellow, this would be the hydrophobic tail. This would be the hydrophilic head, which means that this is the hydrophilic center and the hydrophobic tails. And so you would put a hydrophilic drug in the center, and this would be able to be absorbed in a hydrophobic environment. Here it's U. They modified uracil into pseudouracil, and here's the difference in structure here. So for dendritic cells, they need a high surface to volume ratio. So so they can maximize the surface area that they can make contact with antigens with. And then they can also present those antigens to multiple T cells at the same time, which is really important. And that's why they need that really high surface area ratio. Here, question 10, I got that right. For question 11, these would be small gases. This is sort of a smaller hydrocarbon, so they'd be absorbed very easily. They're nonpolar, hydrophobic. I guess, yeah, mostly nonpolar. But anyway, it's a small gas, so it'd be absorbed very easily, or very permeable. Ethanol, it's more polar. It has the alcohol group, so it's still very permeable, but not quite as much as these ones. Glucose, cysteine. Glucose is a lot larger, has lots of polar groups, so it would need its own transporter. It's kind of same thing with cysteine. Then glutamate, and then these ions. They all have charges. Glutamate would have a charge at a biologic pH. So again, this has a charge, and so they would not be able to go through it all. They would need their own transporter as well. And then I also have the pDNA vaccine, just because it's a very large molecule. It would need its own sort of engineered sort of vessel, something like a engineered virus shell. But yeah, it's not gonna be able to get into the cell on its own. It would need some sort of vessel to transport it in. So I have it at very low. Okay, so for this one, basically it's asking us for the height of the cell culture media. We know the surface pressure. We know the oxygen tension, which means we need the pressure, the pressure at the interface here. And we have enough information to calculate that. So you would calculate this first, and then from there you would rearrange and solve for the height. And that's what I did here. And I did a very similar thing on the real exam. I made a mistake though. I used, I believe, the wrong K value. I used the K value for the PDM or the media as opposed to the PDMS here, which got me a bit of an off answer. Here, I used all the right values, so I got 60, and I rearranged and solved for the height of the media, and I got 991 micrometers, which is below 1,000, to keep the Reynolds number below 1, so this would be an appropriate height. For this one, I got it all right, so I'll skip it. This one, I here, I solved for the volume of the media, which I then calculated the total number of cells, which would be the final number of cells here. This is the final number, and it can only undergo 6-fold expansion. So then I divided that by 6, which is a very similar number to that, but this is cells per centimeters cubed. This is the cells total. So this would be the minimum number of starting cells. Here, you can look here at the doubling time, and then rearrange to solve for K. Then you can plug that in, rearrange to solve for T, plug in your final density, plug in your initial or your final cell number, initial cell number, the K that we solve for, and this will give us the time in hours, so 103 hours about. That's the whole exam. Thank you.